Good afternoon. I want to welcome everybody to the Louisiana Tech College of Engineering and Science Capstone Senior Design Presentations. This particular session is for the students majoring in Instrumentation and Control Systems Engineering Technology, or ICET for short, and also Electrical Engineering Technology, or ELET. Our program has transitioned from ELET to ICET over the past few years, and this year we have the last major group of ELET seniors, along with the first group of seniors who have been ICET majors from the start of the program. I'm Ron Gill, and I've had the pleasure of being the capstone senior design instructor for these students this year. This quarter has been a challenging one, to say the least, but these students have persevered to complete their projects under these unusual conditions. As I've told the students, as engineers, we solve problems, and that's the attitude which they have adopted to complete these projects. This year, the start of the winter quarter, we moved into our new Integrated Engineering and Science Building, or IESB. We were looking forward to hosting these senior design presentations in our new state-of-the-art building, which we're all very proud of. But we had to quickly shift gears this quarter to virtual class sessions and now virtual senior design presentations. So I welcome you to the virtual IESB room 128. On your screen, you can see our schedule for the presentations, which will be spaced at half-hour intervals. There will be a Q&A session at the end of each presentation. We'll use the Zoom chat function to facilitate the questions. To ask a question, click on the chat button on your Zoom menu and type it in. And this can be done at any time during the presentation. Please direct the chat questions to me as the host, and then I'll read the questions for the team members to respond to at the end of their presentation. Our first team's project is the automated dog kennel. Their faculty advisor is Mr. Jonathan D. Morawski. I'll turn over control of the meeting to them now.
Good afternoon, everyone. My name is Alex Shillette, and I am the one who assembled, designed, and helped code the automated dog kennel, or also known as the Good Boy.
Hello, everyone. My name is Kyle Harris, and I helped code the automated dog kennel.
My name is Aaron Hightower, and I helped do a lot of the research for the automated dog kennel.
Hi, sorry, I was muted. My name is Savannah Sims, and I helped conduct research for the automated dog kennel.
All right, so why would you need an automated dog kennel? Well, for one, it would give the owner a sense of ease, as well as calm down any dog with any sort of anxiety problems. It allows for an easier routine, it rewards good behavior in the dog, and it can really assist you in kennel training your dog. It restricts the amount of time the dog can be in a kennel at one time. It can be adapted to any existing furniture style kennels, like you see in the picture on the screen. And for those of us with a busy schedule, you won't have to worry about being late because of your dog. It just helps your dog get in sync with your routine, and all you really have to do is put in what time you're going to be leaving, around about what time you're going to be showing back up, and then all you have to do from there is just take your dog outside and feed them before you leave, and then you're good to go. So with the dog, be comfortable. Inside the kennel, there's going to be there's a removable and washable padding on the floor of the kennel with memory foam made out of 60% polyester, 30% cotton, and we'll have an optional video camera that you can set up to the back of the kennel that will allow you to, optional Velcro, I got ahead of myself there, optional Velcro that helps secure the padding on the floor. And then you can also, we can use like a hard durable plastic for any dogs that may have a lot of accidents or that tear up their bedding. And then with their treat dispenser, you'll be able to remotely give your dog a treat or even feed them from anywhere you need to. Then we'll have some speakers inside that'll help with the automated commands, or you can play classical music or any sort of playlist that you want to put on there yourself that help keep your dog calm.
So our number one safety impact is, our number one concern is the safety of the dog. And so we were able to do that by having the servos. You can move them by hand if there is a malfunction or power loss. Also, you can monitor the dog through the camera that is in the kennel. Social impact. The social impact helps with everyone's busy lifestyle. You're able to, the dog goes in on itself and it's let out by itself as well. And it helps with kennel training. So for environmental impact, we use wood for the full kennel and only use the electrical components for that adaptation kit. Economic impact. It opens up a new market for smart kennels for residential use and commercial use. There's no impact on global welfare, public health, or cultural. And there are no regulations for individual dog kennels, personal dog kennels, but there are some for boarding facilities, but not too much regulation on that.
So the parts that we used were the Raspberry Pi 3B kit that Savannah had gotten from one of her previous classes. We used a Logitech webcam. I believe it was the C270. We got it for about $25 on Amazon. We got the Parallax standard servos, not the continuous, because we had problems with the continuous motors. We had a breadboard, steel wire fencing, steel angle iron, the steel flat bar, 2 of the 4x8x1 blonde wood plyboard, or we just got what we could from Lowe's at the time before quarantine. A stain of polyurethane of our choice, we went with Bombay mahogany, 2 1K ohm resistors, 20 gauge jumper wires, and an aluminum plate for the door and to help make the locking mechanisms for the servos. So the total cost of the full kennel was about $410 with everything. And then the adapted kit for existing furniture style kennels would be around $155.
So how exactly would this kennel work? So you would set a leave and arrival time on an internal timer that we have that you can set through an HDMI screen. We'll show you in a later video. The kennel will call your dog whenever you set your leave time. It'll call your dog within 5 to 10 minutes of your preference before you leave home, which allows you to make sure that your dog's in the kennel before you leave. Once this goes off, there's a speaker with customizable calls. We have a whistle because Alex's dog responded to whistles better, so that's what we programmed it for. And the door is a doggy style door, basically like you would have on your back door, and it is locked at the bottom through the use of servos. Once the door closing process begins, the dog would be rewarded a treat. This actually didn't happen in our project. We had a little mix up. We couldn't get the 3D printers once quarantine started, so we weren't able to print out the actual frame for our treat dispenser. But once this happens, you'll be able to check on your dog throughout the day with a webcam. And if your dog starts whining or getting anxious, you can easily check, play classical music. There are a few studies that show that classical music actually helps soothe the dog's anxiety. When you come home, your dog will be let out 5 minutes after you set arrival time. Chose 5 minutes, so you can set a time that you would like after your arrival time, just to give you a time so when you get home, your dog's not bombarding you if you're walking in with groceries or something like that.
So for the coding, we used Python for the Raspberry Pi. We set up a tkinter main, which we called root. And then as you can see, we have the call time, leave time, and arrival time texts. Then right next to those texts, we have the entry boxes that you can input the values that you want. And by values, I mean the time of day in a 24-hour format, because that is what the Raspberry Pi uses. And then we have the set angle definition. We just did that solely because if we tried to change the duty cycle, there would be problems, and it also makes the servos jitter a little bit. So you would get a constant metal on metal pinging. And we tried to reduce as much noise as possible. So after every angle change, we always set the duty cycle to 0 to reduce the jittering. Then there's also a close and an open button on the GUI, which is the user interface that you can use on the touchscreen. And then there's also the submit button that actually sends the times that you input via the keyboard into the Raspberry Pi code. So this is a video quickly of how everything works. So I had set in the times and then I pressed submit, and I had to do it a minute apart for each. And then I also had to make sure that the speaker was on. And then the whistle goes, and then it waits about 30 seconds, and then it goes again. But this video had to be sped up for time constraints. And right now, you are about to watch the servos actuating. There we go. And so once those servos are actuated, if you come home early, you can press the unlock button on the screen and it'll open the kennel so that you can let your dog out, as you can see there. And then you can close it back whenever you're done. And that arrival time that you set previously will not be changed. So if you come home for lunch because your dog has an accident or something like that, then you can easily let your dog out, clean up the accident, and then go back to your day after you put the dog up. So we have a webcam in there, and I had to take the webcam out of the original casing. And due to not being able to have 3D printed parts, I kind of had to, for lack of better words, just kind of screw it into the top. So this is what you're seeing is the top of the kennel, and it's actually upside down because without that 3D printed holder, that was really the only way that I could have it secured.
So the pros of having a regular kennel is that you can put the dog in at any time and take the dog out at any time. It is a bit cheaper and you wouldn't run into technical issues. The pros for the Good Boy kennel is that it is an automated time for the dog to go in. It calls the dog in. It also will let the dog out at the specific time that you want, and you can also press the button to allow the dog out. It helps with kennel training as well. You can monitor the dog with the camera, and if we had the time, without the coronavirus, we would have had the treat dispenser in there and give the treats as a reward. The cons of a regular kennel is that you can't monitor the dog. You can't see if it's chewing on anything or if it's stuck or anything like that. It does not automatically reward the dogs. It makes it harder to kennel train them. There's no safety features, and it does not save your time in the morning or when you get home. The cons of the Good Boy is that it does let the dog out even if you're not home. It's a little bit more expensive, and there could come technical issues.
So what we have so far as a complete first edition prototype, we have the kennel, which is made out of the aluminum, the steel, and the wood. We have the Python coding for the servos and the GUI, or the user interface. And we also have the schematic for the treat dispenser that's ready to be printed. We just didn't have access to that 3D printer. So this is the skeleton of the kennel with the wire and the flat bar and the angle bar. I decided to put a steel plate in the front because my dog has a habit of pushing against the front of his kennel to try and get out. So I just put that there for my purposes for a little bit of extra safety and a little bit more security and stabilization. This is the progression pictures of putting the plyboard on there, screwing everything in. And this by far is not going to be the last prototype, solely because I had to cut all of this by hand and the cuts were very rough. this is the quote unquote final product. As you can see, there is the Raspberry Pi with the speaker and the touch screen mounted on the front. And then the keyboard and mouse I just have placed on top because I will be using this kennel as an extra work area for like a standing desk. Okay, Kyle.
So what we have for future work are, for the gravity door, we want to add some rubber to the aluminum door for the safety of the dog around the edges, just to make sure that no dog gets hit and cut by the edges. We have to add the hard plastic and cushions for the floor and print the 3D, the treat dispenser. So here we have our schematic for our 3D printed treat dispenser. In our treat dispenser, we kind of just went with, I always look at it as a paddle wheel for a paddle boat. Once it spins, it'll allow a treat to follow every rotation that it makes. And that's kind of the design we came up with, so that the dog would only get one treat as they were going. And then it kind of has this little bowl, so the treat doesn't just fall in the bottom of their kennel and make a mess. It stays in the bowl and kind of makes it easier to clean up and keep neat.
So this was the original design that I had put into SolidWorks. We were originally going to make it out of the 3D printed top, and we were going to have servos and motors to help the garage style door that we had originally set for, but due to time constraints, we had to move towards the doggy style door. There were supposed to be originally infrared brake sensors where the red circles are, to help detect the dog going into the kennel and to make sure that the garage style door did not close on the dog itself. The blue triangle is where the webcam currently is placed and where I thought the best place for the webcam should be. And then the orange square is where the treat dispenser can be placed, but it is all up to you where you want it to be placed. And that is it.
All right, we'll entertain questions at this time. We do have one question so far on chat, and I invite the audience members to submit any other questions on chat and to me, and then I'll read them off. So the first question is, how do you alter the timer settings if the owner's schedule changes and can't make it home as previously planned?
So we have it set on the timer in the program that the dog cannot be in the kennel for longer than 12 hours. So if you're not home in 12 hours, it'll let your dog out, which is one downside, but it's also kind of cruel to leave a dog in the kennel for longer than 12 hours. But you can easily change the time on the front of the HDMI screen and change it to whatever you need it to be for your day. So say day by day your schedule changes, every morning you can set the times differently.
Exactly. And also with that new submission every day, you also do have to check on it every day to make sure that it is up to your original plan. And personally, I would give at least a good 15 minutes plus or minus, well, more added on to how late you usually arrive home, just in case there's a little bit more traffic, if you have to stop by and pick up some milk or something like that. That way you have enough time to get home, do everything that you need to do, and then the dog will be let out automatically, or you can let it out yourself. The one thing that I've really tried to work towards on the timing situation is to where that we can get it accessed remotely as well as the webcam feed. But unfortunately, as of right now, you can only view it on the same server or the same network. So you can have your dog in one room and you can watch it from your computer in another room, but you have to be connected to the same network as of right now. Unfortunately, we weren't able to access the video stream remotely or from a different network because I have Suddenlink and they would not give me the password and all the information that I needed to change the output ports on our modem or our Wi-Fi router. So that was one of the big issues that we had for remote access of the kennel. But we are planning on trying to do that in the future.
Okay, we do have a couple more questions. The next question is, please discuss the hardware used to send text messages.
We did not have any hardware used that sends text messages as of right now. We were trying to, like I said, we were trying to incorporate a remote monitoring system, and through that it would be able to send you an email and or a text message, whichever one you would prefer, on whether or not there's too much movement in the kennel, there's an excessive amount of noise, or if you have a certain if you have someone watching the dog like for lunch, then you can press a button on the HDMI on the touchscreen and it will send you a notification that you need to monitor the dog a little bit closer.
The next question, what was the most challenging part of the project, and did it cause you to alter your approach?
So one of our big problems, we originally did not start trying to use the Raspberry Pi as our programming board. Our biggest problem was we tried to use a board that none of us had experience with in a BeagleBone, and it's a fairly new product. So we couldn't really research widely on the web, on the internet, to find people that have actually tried this and help us in our journey. So come down to the wire, we actually had to change our programmable logic controller, and we had to change our logic in our controller and use the Raspberry Pi.
Also, since we had the design change, that kind of took up roughly around a month of just redesigning everything, making sure that everything was how we wanted it to be. And if it wasn't up to our standards, what could we do as a quick time solution just to have a first prototype to set an example of what we were trying to complete this year.
Okay, next question. Was a two-way video considered as a treat for the dog to see their master?
It wasn't considered, but it is very possible. We could put a screen on the inside of the kennel, but with that, there would be a lot more components. It would be a lot more expensive. And so for a cost-efficient, quote-unquote, luxury item, especially for the prototype, that's what we tried to go for, is something that's more minimalist, but also assists in everyone's daily lives.
Also, dogs have a hard time seeing images on a screen, so it wouldn't really help them calm down or anything like that, or be a treat. We did look into you being able to speak to them too, along with the music. However, that didn't get pushed along because we were having issues with the BeagleBone and how to go from deciding if we're going to use Arduino or the Raspberry Pi.
Next question. What was your inspiration for this project?
I think the biggest inspiration was, it's especially if you have a strict school schedule or a work schedule. I know that personally I've had trouble getting my dog into his kennel. And so I just kind of thought that this would help make it easier and get him into more of a daily routine to where I wouldn't really have to do much, especially if I was in a hurry. Because especially this year, with trying to graduate, senior classes, all the projects that we've been doing on top of this one, I was trying to portray a product that could help me personally, but other people like me in my same situation.
Okay, thanks. That's all the questions, unless some more come in right now, but I'd like to thank the Dog Kennel team, and our next presentation will be the Crumb Cart mobile vacuum starting at 1:30. So we will just take a brief pause here before we resume again with the next presentation. Thanks.
Thank you.
Thank you.
Okay, we'll get started again. And our next project is the Crumb Cart mobile vacuum. And their advisor is Dr. Will Long, and I will turn it over to them.
Hello, can we, everybody hear me? Just double checking.
Yeah, you're good, Brandon.
So our project is the Crumb Cart. Our team members are me, Brandon Trimner.
I'm Michael Bearden.
Yesvik.
All right, so our overall goals were to create a better cleaning version, and along with creating a more cost-effective design, along with possibly being a DIY design. Our goals were to be comparable to the two most common, which would be the iRobot and the Shark vacuums. We also aim to make it more user-friendly and have customizable schedules and remote capabilities of activation. Next slide. Now, we've run into some problems and have had alternate solutions. Some of the problems are, people don't have time to vacuum regularly, or don't have the money to pay somebody to do it, or that the job isn't done properly. The alternate is, do it yourself or hire a premier automated vacuum. Next slide. There's social, environmental, and safety issues. There isn't much on the social side. It would really just be up to house cleaner jobs and that sort of stuff. Safety, there's every now and again, you may hear about a battery pack malfunctioning or catching fire. Vacuums, of course, do at times suck unwanted objects in that can possibly damage them or the item. And some automated vacuums are not too well, don't operate too well at sensing objects and can bump into tables and knock things off. For environmental, it would just be proper disposal of batteries and other components. This is the design for the dust trap. With most automated vacuums that use roller brushes, they don't actually have any kind of suction. They just scrape off right into the dust bin. And they have a cap and a way to capture all of that, of course. Next slide. This is the wheel design we went with. That way we could also put a rubber gasket around the wheel in that slot right there. That way it worked, it operated better on both carpet and tile. And right next to it is the motor mount that we use to mount the motors and wheels. Next slide. And this is the hull design. This was actually the most challenging part to produce, solely due to its size and lack of 3D printers available on campus. I actually had to purchase a 3D printer with a 400 by 400 by 400 millimeter build area. We 3D printed it in 3 sections just in case, just to prevent waste of filament if the print failed. And as you can see, it's just press fit together. Next slide.
For the parts list, we had the Raspberry Pi 3B Plus as our brains for the For the Roomba, we had 5 IR detectors that would detect the walls and the floor. We had 2 DC motors that would run the wheels forwards, backwards, left, right. The fans, the push buttons, the omnidirectional wheel, which allowed for the Roomba to pivot on a point, the agitator brushes, and the battery packs, which brings it out to be about $101, which is a lot cheaper than the average one on the market. All right, and so for the theory of operation, what we use is a L289N H-bridge motor controller, and we use that to control 2 12-volt DC motors that would turn the wheels forwards and backwards. Like I said, we have the 5 IR sensors. There's 1 on each corner and 1 directed downward to detect stairs in case it's going over stairs, doesn't fall down and break. And then there's also the ultrasonic sensor right in the front that allows it to see objects directly in front of it, just in case one of the IR sensors missed it.
So for the theory of operation for our website, because we have, like, as we mentioned, we're going to have an interface so that the user can have input to control it between like when it needs to run, or you're operating remotely for like a spot cleaner, like wall fall, which we'll show you in a minute in our demo video. So this is kind of just like a quick little layout of how the website actually is coded, I guess you could say, somewhat with some scripts, because there's multiple files and how it reads all the information coming and outgoing. You have this index.php file, which is the file that like generates your web page with images and stuff on it, and like gives you a title page and like what the IP address like that is associated with it, gives you like a quick intro into it. So that's like where the index.php file is, like where all that's hosted. This JavaScript file over here is like for clicking action, and we actually like so when you have a click, you actually get like an output of it, so that it actually does something instead of just being a page filled with like an image or something. And then this gpio.php page is like what updates and reads your GPIOs and helps communicate to the Raspberry Pi what needs to go on. And then over here, the Raspberry Pi also generates that information back to the .php. So that's just kind of like the layout for the web, or the first page on the website for the controls. I utilized a application called Webmin to actually like do the automated runtime for our vacuum, and they have a thing in there that's built, or that they utilized off the Raspberry Pi, called Crumb, which is a task manager and scheduler. And Webmin just made that accessible through like onto the web, so that you didn't have to go on the actual Raspberry Pi. Like if you wanted to change when you wanted to run this thing, you didn't have to go on the Raspberry Pi, hook up a monitor and everything. You can do that straight on your computer with all the other controls. And then here's a working video of our project, and Jacob will kind of walk you through that a little bit more.
The project was actually really a lot harder to get it to go back and forth across the floor, like in a certain pattern. So I kind of used the random class in Python to make it kind of just do its own thing, and it kind of just decides when it wants to go forwards, backwards, left, and right. Unless it detects something, then it'll avoid the object as well as it can. But for the most part, it'll just randomly run around the room. And you can see here in the kitchen, it gets a little bit confused with all the different walls, and the IR sensor detecting things from different angles. We also have the wall follow implemented, so it'll go and it'll find a wall, and it'll try and keep the IR sensors detecting that wall on that one side for as long as possible. Right here when we were filming, you can see it gets a little bit messed up here at the end just because of this doorway and the couch right there. It's not really too sure what to do. It kind of gets a little bit stuck right there. And we kind of have the same for the spot clean. It's more like a random spot clean. It just goes forwards, backwards, and changes like its direction just a little bit, just to try and get like a general area. So if you wanted to spot clean like a certain spot in your house, like in front of the door, let's say, you could just go place it down. And since we didn't have the full website working, to upload the code to the Raspberry Pi, I had to go through VNC Viewer and just download it through there and run off the Raspberry Pi from my computer. And then that's what we updated the different things. And here's another video of the random clean. This is like the normal cleaning. And you can see it tries to avoid stuff, but it's still not the greatest. It still has some bugs that need to be fixed, but it is a working prototype at this point. And in a second here, it'll show the inside of everything with all the devices inside. You see the IR sensors pointing down, and the IR sensors are melted into the wall there. There's like 4 of them in the corners. And then there's some wires sticking out the front that attaches to the ultrasonic sensor that I'm about to unplug right there. And so with all those sensors, it's able to detect objects and try its best to avoid them.
So for the last part of our presentation, I'm going to do a demo of our web interface to actually show it's working and everything. As Jacob mentioned earlier, we had a problem getting some of our stuff to actually work together. And that's mostly just being because we were separated. My family wanted me to come home and get out of Ruston, so I lived 2 hours away and couldn't help get all that done, and we just had some major issues getting that actually working on his Raspberry Pi and consolidated onto one. But for the most part, it is all working. So for the first part, let me get this out of the way. So for the first part is just our basic web page that you hit, the Crumb cart controls. As you can see, we have the left, forward, backward, right, and then spot clean, and then the wall clean. They're just buttons that you hit. So as you can see, like when I click it, I have an action that's actually changing, like just that shows that I actually have input. So this is an off state. Everything's off, nothing's going. And as you can see, I have these hooked up to these LEDs right here. All of them are off currently. So if I want to have it go left, for example, I have it hooked up so that this LED's turned on, and I have it for all of them so that you can see that they're all working and that it's fully functional. I didn't have enough LEDs for the spot clean and wall clean, but it's all the same for them. They're all stored in a what I call the data folder of all these images that are populated onto this page, so that each of them has an assigned pin with them for the way this is set up, and that they all work. So that's the basic controls, like how you control it off your phone. It works on a phone, computer, anything that you want that you can have a wireless interface with. It only does work off local, like your local access Wi-Fi router, but we thought that's as far as we needed to go, because it's not like you're really going to be changing this on the fly anytime. And if you are going to be controlling it, you need to be where you can see it. So that's why we didn't go any further there. And then for like the automatic clean, so that like say 8 o'clock every single day, I want the thing to run, because that's when I'm going to be out the house and everybody else is. So for that, as I mentioned, we're using cron jobs. And so for that, this is just kind of how you set it up. So you click on this one. This is the file that I have running the show to work with an LED, and that everything is good. So you have to specify what language, which is where the Python right here. I'm specifying I'm running a Python script, and then the location of that script that's located on the Pi. So I have it in the home folder on a Pi, in that Pi folder, and then the script is, I call it led.py or .python. So then you have to select the times that you want to run. So this is the minutes, hours. You can select how many days in the month you want it to run, how many months, and customize it however you want. So for this quick little demo, I have it set up. So 1343, go. Okay. All right, save. And then go here. Enable it. Oh, dang it. Well, it turned on a little before me, but that's how you essentially use it. And it's pretty straightforward. I mean, there's not a whole lot, and you can run a lot more off of it if you need to. Say like you need to keep updating it, or you need to back all this software up or something. This also allows you to do that. So that's about all. That's all we have in our presentation. Are there any questions, comments, anything?
Okay, we do have a question. What is the estimated shelf life? And if your product was damaged or broken, what would it cost to fix?
I don't really know if there's a set shelf life on this thing. I mean, it could go for as long as you wanted it to. And as for the parts, you can always replace the parts. They're relatively cheap, like DC motors you can buy on Amazon. We bought like a 6-pack of them for like $10 or something like that. The Raspberry Pis are relatively cheap as well, and that's the whole brains of the thing. So if that gets fried somehow, you could just buy a new one of those and have it reset. But like I said, like the shelf life is kind of determined if you're replacing parts or not. So there's really not a set deadline.
So like if it got stepped on, you're using 3D printed parts, you would have to make a new case and of course replace any components that were damaged inside.
Correct. So you would be set back for a little bit to have to print a new case out, but other than that, then it's just assembling.
Okay, let's see. Okay, I do have another question here. Can it recognize stairs or change in elevations?
Yeah, so that's what the IR sensor pointing straight down does. And actually, whenever it detects something not underneath it, it'll stop automatically. I didn't have any stairs at my house to test that out to show y'all, but it was working as detecting the ground when it was just moving around normally. So.
All right. Are there any other questions? That's all the questions that I have at this point. Okay, let's see. Okay. A few more. Does it recognize black objects? Somebody had an iRobot and says that the iRobot did not recognize black objects.
The only black object that I had in my house was the oven in the kitchen, and it seemed to be recognizing that. It did get a little bit closer than that than it did to the wooden cabinets, so that could be affecting it a little bit, but I haven't really seen any other problems considering I haven't had anything else black for it to detect and mess up with.
And next question, what was the most challenging part of the project and did it cause you to alter your approach?
I'd probably say that we had probably two, at least in my opinion. The website and getting that consolidated was not easy because Jacob really didn't know, because Jacob had kind of taken over coding like the scripts and everything for the actual robot to move on its own, and like the scripts for that while I did the website. And so he wasn't like too sure on like how to consolidate that like on the instructions that I sent him. So that was a big challenge for me and him, I thought. I don't know about Michael or Jacob. What else did y'all think was another big concern of ours?
Well, I would say just production of the body would have, was a major issue, but that was due to the Proto Lab. Their one printer that was large enough was down near the end of last quarter, and once the school shut everything down, I had to order one of my own just to print the body out. And unfortunately, it came from a company that doesn't have the best of customer service. So when it arrived, it didn't even arrive with assembly instructions. And so it was. Go ahead.
You can finish if you had more to say.
It was more of a challenge to assemble and get running properly until it could actually complete a print, which took about a week and a half.
Okay, the next question, were the proximity sensors proportional or on-off?
I used the IR sensors more of like a, if it's detecting something or if it's not detecting something. So on off, I suppose. So if it's detecting something, do this. If it's not detecting something, do that.
And what was the range on those sensors?
They're about a foot to like a little bit more depending on if the lighting and everything in the room, but about a foot or less.
And then if it sensed an obstacle at about a foot, then just from observation, how long did it take to react? Did it get much closer than a foot?
It reacted relatively close once it registered something on the IR sensor, it would react relatively quick and it would try to change directions and back up and move away from it. So
Okay, thanks. That's all the questions I have right now, unless we have any coming in right at the moment. Okay, thanks to the Crumb Cart team, and we will take another short break and back at 2 o'clock with the multimeter glasses project. Thanks.
Thank you.
All right, thank you.
Our next team's project is multimeter glasses for a safer way to view a multimeter display while taking readings. Their faculty advisor is also Dr. Will Long, and I will turn it over to the team now.
Hi, I'm Michael Kramer.
My name is Sean Gilbert.
I'm Cody Rogers.
Ryan Cortez. And our project is the multimeter glasses.
First, we're going to show you our video demonstration.
Okay, so these are our multimeter glasses. This is the design for the hobbyist version. It has our OLED screen in front, and then it has a little LED flashlight right there. If I turn my head, you'll see that we have a two switch, one button configuration. The switch in the back connects to the battery pack, which allows you to turn on the Pi. This is a pairing button to connect to the Bluetooth multimeter. And this switch is what turns on the LED that's in the front. Now, if I turn a little bit further, you see this very back piece back here. This is what stores the charging circuit and the battery itself. The battery is a 3.7 volt lithium ion battery, and our charging circuit is so that way you can charge this at the end of the day without turning the powering the Pi back on, and just make sure that the battery gets recharged. Now, if you see, they fit pretty comfortably against the side of my head. They look a little bulky, but they're really smooth against the side. And if I shake a little bit, they don't really go anywhere. No issues there. Also, this piece is telescopic for people that have different like eye troubles and whatnot. You can kind of adjust it in order to have different visual levels and stuff like that. Next, we're going to talk a little bit about the hard hat version of our project. Okay, so this is the hard hat variation of our project. It still has the same screen, and then it runs up to this connector. Instead of it all being like one telescopic piece, what we did for more flexibility was have this loom that connects to where the Pi is housed. There's also, instead of an LED flashlight, we have a camera. That way you can record operations performed at the panel, and you can actually twist this camera a little bit. That way you can get better angles. We have this little slider piece in order to adjust where the screen is on the actual mount of the face shield, in order to change the positioning a little bit if, you know, maybe you have better sight in your peripherals or whatnot, stuff like that. Now, if I turn a little bit, we do have the same button configuration and switch configuration, where there it is. One switch is to turn on the camera this time. We still have the same pairing button, and we still have the same power switch. Now, instead of a battery pack with a charging circuit, we have wired it so that this loom runs to the OLED headlamp, and it connects to the Pi directly through that switch.
First, we'd like to start with an overview. On average, there are approximately 30,000 arc flashes a year. Unfortunately, 400 of those result in fatalities. These glasses will allow the user to have a safe location to store their multimeter while conducting various tasks within a distribution panel. This device is a heads-up display that would allow the user to maintain focus while simultaneously providing the readout at a glance. Next, please. Now, some additional key features of this device will include a flashlight, a camera, and an integrated Wi-Fi development board that will send the readout and camera data online via email to the user. Some safety concerns of this project include eye strain from prolonged use, and in the case of an arc flash, the PLA frame will begin to melt at 350 degrees Fahrenheit, while the lithium-ion battery will malfunction at 140 degrees Fahrenheit. Now, disclaimer to all our users are, these glasses are meant to reduce the actual chances of an arc flash occurrence. Now, however, there is not currently a foolproof method to completely prevent such incidents from occurring. Next, please. Now on to our environmental and social impacts. Recyclability is our major environmental concern. The PLA frame can be melted down and extruded into filament for later projects. Our PLA is biodegradable, which starts at temperatures over 140 degrees Fahrenheit. And our lithium-ion battery is rechargeable and can be recycled for its lithium. And lastly, the primary social impact of these glasses is to reduce the chance of an arc flash occurrence. Now on to Cody with how it works.
So a little bit about our project and how it actually functions. So we have our PLA frame, and it's lightweight, it's strong, it's water resistant, and it insulates all of our components. We're powering our device with a 3.7 volt lithium ion battery. So whenever you originally turn the Pi on, there's that pairing button on the side. You hit that and it connects to the Bluetooth multimeter. Next, please. After the Bluetooth multimeter has actually been paired to the Raspberry Pi and it starts taking data, this data will be transmitted to the Raspberry Pi. This data is then stored there until it can later be sent online via email. But while it's being stored, it's also being displayed onto our OLED screen. All of the operations performed at a panel, can be recorded using the camera on our hard hat variation in order to make things such as training videos. And then for the hobbyist version, we have a flashlight in order to provide extra light. And we also have the charging circuit. That way you can plug in the hobbyist version at the end of the day without having to turn the Pi back on. Next, please. And over to Ryan to talk about the programming.
So we first started programming with the screen in Arduino to figure out how the screen worked. So using a program that was provided by the company that we got the screen from, we looked through the program and saw how the program reads hex code to tell the screen what pixels to turn on. So we took a picture of our favorite teacher, and using an online converter, we converted the picture to a bitmap. And using a software that came from the company we got the screen from, we put the bitmap into the software and it produced the hex code. And at the bottom picture shows what was produced on that screen. Next, please. So next, I was able to find a program to be able to design the numbers and screen layout shown on the right. On the left is just a small section of the hex code that is shown on the right. All of the bolded hex codes are instructions telling the screen to turn on a specific combination of pixels. For this screen, each code is 1 pixel high by 8 pixels long. Next, please. This is how the program will flow. So we first started our program in Arduino, which with the help of our advisor, Dr. Long, we were able to convert that Arduino code to Python so that we will be able to run it on the Pi that we're using. So our program starts with the setup, which is where we declare all of our variables and set up the connection to the screen. From there, we move to a while loop, which will run until there is a statement that breaks that loop. So first in the loop, we have the multimeter part of the program, where after clicking the pairing button on the glasses, the Pi will connect to the multimeter and will begin taking readings. When the multimeter receives data that is not a no-load reading, it will be stored in a CSV file in the Pi. And when the multimeter stops taking readings, that file will then be emailed to the user.
Sorry about that.
Next in the loop is the screen display, where when the Pi receives the data from the multimeter, it will then be mapped to what number is being shown on the multimeter to the screen, and it will also indicate what units it's reading, such as amps, volts, and ohms, as well as the prefixes like milli or micro. And I'm going to hand it off to Michael to talk about the design.
So our project has two different, like has been said before. We have the low power design, which is mainly for hobbyists, general workers, and contractors. It's a simple and lightweight design with mostly interlocking pieces. This is due to we wanted to reduce the number of fasteners needed. So first, up here, this is the battery compartment, a little bit on inside. We have tabs to keep the components in place without having to use the fasteners. So the battery is going to go here, and it brings the wiring through here to the charging circuit. And this is the main body. You can see the tabs here again. It holds the Pi in place. All of the wires run through the central channel. As you can see, go straight through from front to back. And this version is also meant to fit on most pairs of safety glasses. This can slide on any of the pair of safety glasses, and without having to be tightened down, it fits on your face securely. Here's a close-up view of the button and switch placement on the main body, and also of the LED on the telescopic rod. Now for the high power design. This is made to fit comfortably on top of a hard hat, and it's designed with these tabs here to snap into the hard hat slots and to keep the headlamp in place using these tabs on both. On the left here, you can see the button and switch placement are the same. All this basically the same design as the hobbyist version, with slight changes for the power to come in this way and the cords going to the screen and also to the camera coming out this way. You can see it up in use version. This if you look right here, you can see how the rim rider connects, and you can slide it all the way around as far as this cable will let you. Again, the real life of the button and switch placement and how it holds the headlamp in place. Now, to the model of how the camera and the screen connect, you can see this camera can swivel in 360 as far as the ribbon cable will let it. And it is attached to the rim of the face shield. Again, the camera can be positioned in any way that you want to point it. Over here, you can see the connection from the main body to the screen and from the battery pack of the headlamp to the main body. And then a little closer, the camera. And I'm gonna pass it back to Ryan for the schedule.
So this is our project schedule for this quarter. And our main objectives for this quarter was circuitry, programming, and designing and printing for the hardhead version. And we were able to complete all of those for this quarter. And I'm going to hand it back to Sean to talk about our difficulties.
Now, in terms of difficulties, with space, all of the features we wanted to include required a decent amount of space, which was a limiting factor in our design process. In terms of modeling, we are currently on our 7th iteration for our design. Now, in terms of our PETG, this material had a higher heat resistance, chemical resistance, and is also waterproof in comparison to the PLA. Now, however, the 3D printer we used struggled with printing the PETG. And in terms of the Pi Zero W, due to lack of experience and knowledge, it was difficult to implement all of this in a timely manner. Now I'm going to pass it on to Cody.
All right, so as far as our future developments and what we would do differently, we would actually like to stray away from our Raspberry Pi Zero W. We understand that it's probably better to handle the bulk of our project. However, due to its 32-bit operating system, there's a lot of libraries that do not have 32-bit versions, so we had to kind of work around that and figure out what to do. Another thing, and so instead of the Raspberry Pi Zero W, we'd like to move to a Wi-Fi Bluetooth module with an Arduino Pico configuration. This would make our project's frame smaller. It would allow us for greater customization, and it would increase the battery life of our system overall. The Pico would be specifically used for our camera, and we do understand that most Arduino cameras cannot handle color video. However, we do believe that a good training video can be produced in black and white. And for the Wi-Fi Bluetooth module, it works very similar to an Arduino. It has GPIO pins and things of that nature, so that could take care of all of our other functions. And we want to alter our OLED display entirely. We had problems from the code, like Ryan found those programs and stuff like that. However, we think that one that would be flexible and have an adhesive property, that way it could be easily stuck onto the face shield or the lens of glasses would be better. Are there any questions or comments?
Okay, I don't have any questions submitted yet. If anybody that's viewing has questions, please submit them on chat just by clicking on chat and typing it in, and then I'll read them off. The one question that's been asked of every team so far that you pretty well addressed already, what was the most challenging part of your project, and did it cause you to alter your approach? Do you have anything to add along those lines?
I know for Michael, I don't know if there's anything he would have done differently per se, but he went after iteration through iteration to make sure that, because we have the old copies and the old designs, we've kept all of them just to make sure that we don't need to regress and then go back forward again.
Definitely going with the Arduino system, because the Raspberry Pi was huge and it runs the battery down really quickly, and it's also really slow to boot up.
Okay, we do have some more questions here now. Can Journeyman line transmission or distribution use this project?
This was actually, the idea was, I worked for Haynes International this summer, and they were really interested in it, and that's the whole reason we made it. So we were planning on continuing this project in the future to for these companies like the Journeyman
Next question, how many individual 3D printed parts are included in your prototype?
Ooh.
For the hard hat variation, there is six major parts, and then for the hobbyist version, I think it's also 6 as well, maybe 7. And they do all. I have the model here with me. Actually, they do come off pretty easily. Now they are like ceiling tabs, but everything like this is the telescopic piece and whatnot. So it's not a whole lot of parts that you have to slide in and out. And once they are together, we actually had intended to hot glue them, and we did at one point, but we needed to change stuff, and we didn't get back around to gluing them back together.
In the future, I'd really like it to be injection molded, or printed in more like less pieces, so we have less that has to be printed.
Okay, next question. Why did you choose the Raspberry Pi 0W?
So when we initially started, we had actually wanted to use an Arduino Nano, but we did want to add as many features as we could, and one of those things was the video that we were talking about, and that's what we learned, that the Arduinos weren't really good for handling video, and that the Pis were better. And so that's like one of our major reasons. And then also we figured that it might be a better challenge, and because we know the Arduino very well. And like we said, the Pi is something that we're a little bit less knowledgeable in.
Next question, how would you accommodate the heavy gloves electricians wear when operating around high voltage?
Certainly by redesigning it a little bit, making bigger buttons and switches, making it a little more accommodating, depending on how heavy the gloves have to be, how or the dexterity that's required. It's mostly pretty easy without the gloved hand or with just light gloves on right now, but designs would be changed in the future to accommodate for that.
Next question, since the Journeyman line can use this product, have you considered using solar resources to help power your product?
I had not, but I've definitely taken into consideration now.
And it looks like that is all the questions right now. So I'd like to thank the team, and we will resume at 2:30 with the Pioneer. Thanks. Our next team's project is the Pioneer. They call themselves the Pioneers because they're the first group of graduating seniors who have been ICET majors from the start of the program. Again, if you have questions about the project, please submit them using the Zoom chat function. And here are the Pioneers.
Hi, everybody. I'm Brandon Navarre.
I'm Jacob Fredericks.
Brandon Navarre. And I'm Tyler McCullough. And we present to you the Pioneer, an automatic wire measuring, stripping, and cutting device.
So in the ICET program, our curriculum consists of, it's very focused around project-based learning. So in many of the classes that are included in the curriculum, throughout the quarter, the student will actually put together a project and analyze that project and work with that. And so at the beginning of each quarter, the student actually purchases a kit from the Office of Project-Based Learning that is put together that includes everything required to put that project together. So at any given time throughout the year, there's always either student workers or student volunteers working in the Office of Project-Based Learning, putting together kits in large quantities, sometimes hundreds of kits at a time. And so one of the most time-consuming parts of putting these kits together is actually cutting the wires needed for the project to length and including them in the kits. So what we've done is we've created a device that totally automates that process, saving time and therefore saving money. So this is the final product. As you can see, it's meant to be on a countertop. It has a 4-inch touchscreen HMI at the top there. And right below the HMI, you can see what we're calling the electrical frame, where we house all of our motor drivers, our logic controllers, and our power supplies. To the right of that is our mechanical frame, where all of our motors and gears and moving parts are housed. So the interface of the machine was a very important aspect for us from the very beginning. We wanted to make it very easy to use so that nobody would require any training to use the machine. It has a 4-inch touchscreen interface at the top of it so that the user can interact with the machine. It consists of very few buttons so that the user is not overwhelmed with a large amount of settings or options or anything like that. And what the interface allows the user to do is submit a quantity of wire and a length of wire, and whether they want the wire stripped or not stripped, and submit the job. And one of the good things about the interface is it includes a job queue, which allows the user to submit multiple jobs to the queue and stack them on top of each other so that the machine will automatically perform these jobs back to back without any further interaction. So this is an example of the two main screens that the user will be interfacing with. At the top, you see the home screen, and that's always visible on the machine. And at the bottom, you see our job creator screen. This screen is where the user will actually insert a job and tell the machine how many wires and how long and if they're stripped or not. And this is a video demonstration of the user actually going through and putting some jobs into the job queue. If you want to play that video, Tyler. As you can see, there's only 2 buttons on the main screen. And from here, the user can go into the job creator by selecting submit a job. He can select a quantity of wire by inputting using the numeric entry box. Once he presses enter, he can select a length value, and the length value allows the user to input up to 2 decimal places. And once he's input his length value, he can then select his units from the selections there to the side, and whether he wants the wire stripped or not stripped, and submit the job. So it goes back to the home screen, and you can see the current job status box pop open at the bottom left. And from here, the user can submit another job, the same as before, select a quantity, a length, and whether the wire should be stripped or not stripped, and submit it to the queue. And this will add the job to the queue. As you can see on the home screen, it says 1 job in queue. And from here, we're going to go into a fast-forwarded view of the user inputting multiple jobs into the queue all on top of each other. So same as before, quantity, length, stripped or not stripped, and it adds it to the queue. There can be up to 255 jobs in the queue at any given time, and the machine will go from one job to the next. As you can see, it says 3 jobs in the queue currently, and it just went from one job to the next job. Now it says 2 jobs in the queue, and the current job status box is letting the user know that it's currently working on a job that consists of 25 4-inch wires that are not stripped, with a live update of the percentage complete with the current job that it's working on. And when the queue runs out, once the machine goes from one job to the next and the queue runs out, it'll show a message on the home screen showing the user that there's no jobs in the queue.
So here's some design goals that we have achieved throughout the process of making the Pioneer. Number 1 was safety. We wanted to keep it to where no one can really get their hands in there, but if you need to access it, you can easily. We knew that multiple people would be using it. So, and we have a lot of moving parts like the blades, the wire stripper, and wire being fed into there. So we want to try to keep it as safe as possible and eliminate any hazards. Durability. We built the Pioneer to last a long time, to be actually used for years to come. It wasn't just something that we put together and was going to be thrown on the side. We believe Dr. Hall is going to actually use it to make all the kits, like Jacob said earlier, for the freshman kits and just engineering in general. Reliability. We built the Pioneer to be very accurate, to be very reliable. Whatever you put in is what it's going to spit out. Easy to use interface. We made the touchscreen interface where anybody could walk up without prior knowledge or teaching could use it. They could submit a job effortlessly and have everything come out the same. We try to avoid using 3D printed parts. So we tried to buy stuff offline or repurpose things from like known things like 3D printers or other things. The speed of the machine was key. We wanted to be faster than a human, and we achieved that. Some key features that I want to talk about here is the rack and pinion. We designed it ourselves. We actually designed the rack on SolidWorks, and that will be discussed later in the presentation. We use an extruder feeder, and we got the idea from a 3D printer, which actually helps feed filament into the 3D printer. And this helps us feed the wire into our machine. We implemented some stripping pliers, which I'll show on the next slide. And that allows us to strip the wire effortlessly and allows us to strip and cut the wire. We used 2 different power supplies, one for the mechanical and one for the electrical. And that allowed us to add some safety measures, which will be discussed later. We used 3 stepper motors, one for stripping, one for feeding, and one for cutting. And those are very important to the project, and that will also be discussed later. We implemented a linear guide on the rack and pinion design to help it move smoothly up and down in a linear motion. Tyler, you can go to the next slide. So here's a picture that depicts the mechanical side of the Pioneer. So as you can see on the right, we have the stripping pliers. And you can see as the wire goes through the stripping pliers to the extruder feeder, which is that red thing on top of that stepper motor. And that goes to our rack and pinion, which is hooked up to a geared stepper motor, which gives us enough torque to cut the wire. And as you go down on the stripping pliers, you can see where it's bracketed using a wire to another stepper motor, which allows us to strip the wire.
In this video, we wanted to highlight the homing sequence of the Pioneer. If you start the video, Tyler. And at first, I think right now we'll be inserting a job, and then it will begin the homing sequence. And that entails the blades slowly moving upward until the limit switch is initiated in the red bracket. And then it will tell the machine that the blades aren't in the way and the wire can proceed through, so they won't get jammed up or anything. And this will happen before every job. And then behind the rack, you can see the linear guide, which has 3 wheels on it to allow frictionless motion up and down. So there's no added friction on the rack and pinion. So all the torque's kind of going into the wire to be cut. In this video, it's a good shot of our blades and rack and pinion meshing together and just cutting wire. You saw the homing sequence started, and then it cut a little extra off that would be in the way of the measurement, so the measurements could be accurate. And actually for this rack and pinion, we had to design it ourselves, the rack on SolidWorks, and then get it cut on a water jet cutter. And the cut wasn't too good, so we had to actually take some jeweler's files and file the teeth on the rack so they mesh properly with the gear or pinion. And as you can see, it cuts fairly effortlessly and pretty accurately, not a jagged cut. And here's a good shot of the entire mechanical side in action. We'll start with a homing sequence, and then after he submits a job, and then as you can see to the right, the stripping pliers, the feeder motor in the middle, and then the blades to our left once it starts. But the stripping pliers will nick the wire, and then the feeder stepper motor will know exactly where the nick is at, so it'll be able to feed it to the blades, which will then cut the wire. As you can see here, starting to happen. And then the bottom bracket for the bottom blade, we also had to machine that and get it cut on a water jet and then recess the blade in it, as you can see. So everything would be lined up appropriately to make a smooth cut on the wire, a nice even cut.
So here we're going to talk about some of the electrical design and safety of the machine. So we added a picture here of some of the electrical components. And starting to the left, you see a big gray box. And this is a programmable logic controller, or known as a PLC. And what this does is lets us program and code the machine to tell the motors when to actuate and how much they should actuate. And it's basically the brains of the operation. At the bottom of the picture, you see here a few stepper drivers. So every stepper motor needs a stepper driver to go along with it. This gives us the options for pulses per revolution on the motor, as well as a current rating for the motor. As mentioned before, we use 2 power supplies, and this is for one, making sure that we have enough current for all of the components on the machine, as well as 2, separating the electrical and the mechanical systems on the machine. So the one on the left is electrical and the one on the right is mechanical. And what this does is lets us do safety measures later on that we will discuss. Everything is 24 volts from the stepper drivers, the stepper motors, the PLC, and the HMI. So some safety things that we had to include were obviously an e-stop. We had a bunch of moving parts, a lot of meshing gears, a lot of pinch points, and we didn't want anyone to get their hands caught into the machine or have some clothing stuck. So we had to implement an emergency stop, as well as if the machine were to bind up on itself, like if the blades were to get caught on one another and you had to quickly stop the machine, the emergency stop is great for that, which we'll show soon. And acrylic casing, that goes forth with preventing people from getting clothing or body parts stuck in the machine. So here we have a video of the machine is going to start running. You'll see the linear motion start, and we would just kind of assume, hey, something happened to the machine, someone's clothes got stuck, and you shut on the e-stop and it shuts off the mechanical side very quickly, as well as leaving the electrical on. So you want to leave the PLC and the HMI running, because if it were to be like a minor issue and you wanted to quickly restart, you don't want to wait on the PLC and the HMI to have to reboot. So that was just one of the key features. And you see the acrylic here. We had mentioned we wanted to keep 3D printed parts to a minimum, but you see these brackets are 3D printed. That was a cost design, kind of keep the cost low. So there are a few parts on here that are 3D printed. Going forth, here is reloading the machine. So I guess some questions might be about how easy is it to reload the machine, or how effective is it, and how easily can the wire flow through the mechanical design. So we wanted to show that, as well as the sliding door for reloading. We used the grooves on the extrusion to kind kind of put acrylic into it and make it slide real easily for easy access, but still it has a safety measure to it. So it's that easy. You just slip the wire in, and we're showing how effective and how quickly you can get results from the machine. So some people might ask if it's even worth it to input a job if you only have, say, 10 wires. And we're kind of trying to show how quickly, this machine can do 10 wires. It can do a small amount and a large amount faster than a human. Also, in the final product, we have a catch bin here. Some things that we discussed were how to make it better. And we thought about making a ramp right here, going from the blades out of the machine to where your wires would fall into a catch bin outside of the machine so that you could prevent having to stick your hands in the machine at all. That was just one of the key features that we had thought of afterwards.
So here's some statistics of the machine. It's able to cut 1 2-inch wire per second, or 62-inch wires a minute. We wanted to keep it where you just put it on a table, like a desktop version. So the footprint's around 1 foot, 1.5 foot by 1.5 foot. It weighs roughly 30 pounds, which may seem heavy, but we think it's perfect because it keeps everything grounded and where it's at and allows it to work properly. It's accurate up to 1/10 of an inch. And we did some tests where we just had one person trying to cut wire and the machine going, and we found that it was 10 times faster than a human. And also you can see on the right, there's a picture of some of the finished product, the wire. And as you can see, it's stripped, and it'll allow the user to just easily pull out the insulation and plug it into their breadboard or whatever their project is. So here's the project cost. As you can see, we have it all labeled out here. We have our electronics, our hardware. We have some more pricey items, our PLC, which is around $370, the touchscreen interface, the HMI, $276. Everything in red is what we had to pay for ourselves. And the cost per teammate came out to around $50. And the total cost of the entire project was $1,100 around.
Thank you all for viewing the project, and questions will be answered through the chat. Thank you.
Oh, we can't hear you, Mr. Gill.
Yeah, sorry about that. I unmuted. All right, as Tyler mentioned, we'll entertain questions through the chat, so please submit those. We do have one to start here. Have you considered modifying your product to assist power utilities to cut their distribution and transmission wire?
I believe that we're kind of trying to keep this to a smaller gauge, so like 22 gauge. From what I know, transmission and utility lines are in the much larger range. There is a product similar to this, and it's called the Stripmeister, I believe. That's for like heavy duty cables and such. But I don't think this machine would cut very large wire. Anyone else have anything they think?
I mean, we'd have to change like the blades and the motors,
Theoretically, the design would work. The design would work for larger wires, but we would have to basically upsize every part of the mechanical side.
Right. So it is possible, and the design is there.
Okay. How many person hours do you have invested in this project?
Quite a bit.
A lot. Yeah. Man.
It'd be hard to say how many exactly.
I'd say we worked on this like all four of us about 3 to 4 days a week for anywhere from 2 to 4 hours at a time.
Yeah.
The course of the year.
Probably 20 man hours a week.
Yeah, I was the faculty advisor, and they didn't need much help from me. And I know that I saw them when we were meeting, when we were still on campus for the first 2 quarters of this school year, that they were, I saw them together working on the project quite a bit. So Yeah, I can certainly appreciate all of the time and effort put in, and it shows.
So thank you, Mr. Gill.
The most challenging part of the project, and did it cause you to alter your approach?
So the most challenging part was definitely stripping the wire,
Yeah.
and it did cause us to alter the approach and our design. Originally, we had planned to use the V-shaped blades that we use for cutting to also strip the wire and also pull the insulation entirely off the wire. The problems that we faced with that were we couldn't grip the wire hard enough to pull it through the blades without damaging the insulation along the length of the wire. And we played around with it for a little while, and we were able to get our original design to work, but not reliably, not 100% of the time. So that caused us to go with the stripping pliers that we showed earlier and a deliverable that required the user to just pull the insulation off the end of the wires.
Next question, you mentioned the 22 gauge wire. Have you tried any other sizes, and what would the range of wire size be that it could cut?
Well, a perk to, as Jacob mentioned, as to the stripping pliers, is that those stripping pliers don't really care how big the wire is. So that's definitely an advantage. So we wouldn't have to make it programmed differently for the blades to actually come down any different distances for different wires. It would be a feeding problem at that point through the extruder. But no, we have not run any different size wires through. It's pretty common. This machine was built for the engineering department, Dr. Hall and Miss Ashley Osborne. So a common wire there that they use and give out is 22 gauge.
We have several more questions. Next, when reloading the machine, how do you know how much to feed it in order to properly load it, therefore causing the first cut after reload to be a scrap piece?
Pretty much, as long as you have to reload it past the blade. So at the beginning of every job, for that exact reason, in case the user had just put more wire into the machine, the first part of every sequence of every job is for the blades to come down and cut so that it nicks or it cuts that bit of wire, and the machine knows the exact length of wire in the machine.
Next question, can the blades on the V cutter be sharpened, or would they need to be replaced? How difficult would maintenance and repair be on this machine for a normal user?
They certainly can be resharpened. I think they are stainless steel blades or hardened tool steel. I'm not sure exactly which one. They're fairly expensive, so you wouldn't want to rebuy them too often. So definitely resharpening. And then the homing sequence would allow you to know exactly where the blade is at all times. So it shouldn't pose a problem if you were to resharpen and kind of take a few microns off of each blade.
And the reason why we went with the more expensive blades is so that they wouldn't dull as quickly.
Right.
Mm-hmm. Also, we tried to make everything accessible and adjustable. So if anybody had to go in there, change out a stepper motor burnt up, they'd be able to get to it, take it out, and put a new one in.
Yep.
Easily.
The next question, how much of this project was assembled on campus?
70%, 75%.
Some of the mechanical frame was all mounted on campus. The acrylic work was done after we moved to online, and the stripping pliers were implemented after we moved to online. But a vast majority of this was put together before this quarter.
Okay, next, what's the failure rate? How often does the machine jam, misstrip, or miscut? And why did you want to avoid having to use a 3D printer?
Well, we wanted to avoid using the 3D printed parts because we didn't want wear and tear on those parts. We didn't want, like we said, we wanted this to be used for a long time and not have to be maintenance frequently by any means.
Yeah.
As far as the failure rate of the machine, I don't have an exact number. I do know that sometimes the length of the strip is slightly uneven, but as far as the length of the cut, the wire length is very accurate and very consistent.
And also, some of the 3D printed parts that we used aren't critical parts, aren't too like they're not holding weight or anything like that. Just holding the top at a 20-degree angle facing up to where it's easy to see. And then we 3D printed a mounting box for the stepper drivers to sit inside.
And the type of filament we use, PLA, it can, due to flexing, it can get very brittle. So we didn't want to use it too much in the entire project.
All right, the next question. Have you thought about combining this in some way with a 3D printer to embed conductors just for future product development?
Like putting wire inside of a part that's like currently being printed. I haven't thought of that. I don't know if any of the other guys have.
It's not really something we considered. It's definitely a very interesting idea.
That is an interesting one.
And another question, any different wire insulation types used?
No, just one. Just one.
None that we've tested it with.
And the reason for that is that the purpose was for the wires that are used in the mainly the 120 series classes and circuits on campus.
Yeah, that was one of the good things about designing the project is it had a very specific purpose. We knew all along what we intended for this machine to do.
Yeah.
Next question, will you patent and sell your machine?
Gonna think about.
Yeah, something to think about.
Yeah.
There's a few things in there that we thought were clever. I don't think it's ever crossed my mind to patent any of it.
Yeah.
Okay, so we are just about out of time and we are out of questions. So certainly we had a lot of questions here that there was a lot of interest, and we will take a short recess here and resume at 3 o'clock with the Smart House. Thanks.
Thank you, Mr. Gill.
Mr. Gill.
Thank you, Mr. Gill.
Thank you, Miss Ashley.
Mr. Gill, are we ready to go?
Yeah, okay. I need to stop sharing my sheet. The next presentation, the project is the Smart House, and go ahead, Zach.
Good afternoon, everyone. My name is Zachary Ledoux.
I'm Jackson Newman.
And I'm Matthew Fuller, and this is the Smart House. So the goal of our project was to create an energy efficient and economical example of modern home automation. And we did this by monitoring and controlling the lighting and temperature system of a small scale home. So we can do this either on site or anywhere via mobile device using the IoT platform. So our project incorporates what is called IoT. IoT stands for Internet of Things. It allows objects to be sensed, controlled, and collect data remotely. The form of IoT that our group used is called KENNEL, and it allowed us to control and monitor our home anywhere using any device connected to the internet. And so when we connected to KENNEL, it allowed us to use different buttons, graphs, statistics, all of that kind of stuff to monitor and control our project. So one half of our project is a physical component, and this is the mock house that we built using a aluminum base frame. It holds a light bulb, fan, and other components that are used to basically control those two things. And all of it is wired and controlled using an ESP8266 microcontroller. So here's our parts list. As I mentioned before, the ESP microcontroller is basically the brain of our house. It's a single most important component of our project. And it can control our photoresistor, our temperature sensor, and in turn, those control the DC fans, the light bulb. And we also incorporated relays, diodes, and transistors to make the switching easier. We'll talk about that a little bit later.
And this is our construction of our project. It's made from extruded aluminum and pieces of 10 by 15 by 15 inches. And as you can see in the bottom of the left-hand side of the video, the picture, there's a little gap between the main part of the frame and the bottom part, and that's going to control or hold all of our circuitry, so that way it's out of the way and it's not cluttered, and it keeps everything, you know, looking neat and professional. And on the right-hand side of the screen in the picture, you'll see this is a picture of our extruded aluminum frame being cut. And then this is another picture of us constructing the frame of our smart house. And you will see that 2-inch compartment on the bottom of it. And in the left-hand side of the screen, or the right-hand side of the screen, you will see a piece of sheeted aluminum. And that's going to hold all the circuitry, and it's going to be mounted to it. So that way everything is, you know, it's in a stable environment. So that way nothing's moving around and everything's secure, and keep everything out of the way. And the top picture in the left-hand side of the screen, you will see it was made in AutoCAD, and that little ball thing in the top of the picture, that's the light bulb for our smart house. And that little box on the left, towards the right-hand side of that picture, the same picture, it will be the fan. And then the bottom picture in the left-hand side of the screen is just a different angle in AutoCAD that we took of our smart house. And on the right-hand side of the screen, you will see the finished product of our smart house. It has all the circuitry, which holds the ESP8266 microcontroller, the relays, the Arduino that we use for a different power source, and the light bulb and the fan. And that's our completed product for our smart house.
ESP8266 is a microcontroller that gives us the capability to connect to the internet via Wi-Fi. Because of this, it allows us to monitor and control our system remotely. The ESP8266 has multiple input-output pins, which allows us to connect to a variety of different devices. And it also runs on Arduino IDE, so we are able to write and program our system in Arduino. So the two sensors that we use for our project are the Dallas temperature sensor and the photoresistor. The Dallas temperature sensor is a digital temperature sensor that provides a 9 to 12-bit temperature readings and is more accurate and reliable than a thermistor. And the ESP also only has one analog pin, so the Dallas temperature sensor kind of fits perfectly in this. The photoresistor is an analog light sensor that's used to detect levels of light in a given area. And the two reactive components of the project are the fan and the LED light. The fan is a PC fan that's used to replicate an HVAC system of a house, and the LED light is used to replicate the lighting in the house, as well as being used for its cost efficiency. And since the ESP has a maximum voltage output of 3.3 volts, we have to use an external 12-volt power supply to power the light and the fan. So in order to control the fan and the light under a different voltage, we use relays, the diodes, and the transistors to turn the components on and off. And this is done by sending an electrical signal from one of the ESP output pins to the relays, which then either open or close a 12-volt circuit to the components, which turns on the light and the fan, or turns them off.
So this is a little diagram of our circuit. At the top right-hand corner, we have our two voltage sources. Like Jackson just talked about, the 5-volt source is powering both controllers and then powering both sensors. So they send signals, like you're saying, the photoresistor is analog, so it goes to an AO pin, which the ESP only has one, and the temperature sensor sends to a digital pin, and the 12-volt supplies to each relay so that it can turn on the light and the fan. This is some pictures of the code. Up here at the top, we have logging into the Wi-Fi and then logging into the KENNEL website. And then it's basically running the protocols and configuring the sensor, and then the conditions to when to turn the fan, the light on and off. This side is the fan side. It has a little bit more than the lighting portion. You have to kind of set up the sensor so that it can output in Fahrenheit, and then it's just similar down with the conditions. This is a little picture of the KENNEL home screen. In the two left side, we have places where it'll output the values of the sensors, and on the right, there's two buttons that we can control the light and the fan. So this is a video. First one is for our lighting portion, and the second one for our temperature. Out here on the outside, I have a photoresistor. This relay can turn on the light. This temperature sensor right here, it talks to this. And then it goes to the purple wire. This relay.
Zach, we can just barely hear the audio.
A little better. So we use this Arduino to power the whole circuit.
Yeah, that's much better. Why don't you take it again from the start?
Okay, sorry about that. I didn't realize it was quiet. My name's Zach. I'm going to talk about our physical portion of our project. So here we have our two ESP8266s. This first one is for our lighting portion, and the second one is for our temperature. Out here on this outside, I have a photoresistor that's connected to the first ESP, which is then will send a signal to this relay and turn on the light. This temperature sensor right here, it talks to this ESP, and then it goes from this purple wire to this relay up to the fan. I'm gonna turn it on. we're using this Arduino to power the whole circuit. This side here is giving 5 volts, and this other side is 12 volts. The needed. So the ESPs send the signal to the transistors, and then they switch on the relays, and then it sends that 12 volts up to the components. So, talk a little bit about the lighting. This photoresistor, it gives us an analog value. If the value is under 500 ohms, it'll turn on the light as it is right now. When I shine my light on it, it'll turn the light off and back on again. For our temperature, it sends a digital signal to the ESP in Fahrenheit. Once it reaches 75 degrees or higher, it turns the fan on. It turns back on when it gets back under 73 degrees. Here on Cayenne, you can see this is a real-time values, but 74 degrees Fahrenheit and has 88 ohms. Here I can on here, and it gets above 500, turns off. The temperature just reached below 73 degrees, so it turns back off the fan. I can do a little bit of the code here. These ESP826s are Wi-Fi capable, so they have these type protocols to be able to connect to the internet and then to Cayenne. And here we log into the website and setting up the sensor. And down here we have actual sending the values, and then we have our conditions here is the 75 and the 73.5. And this code is for the lighting portion, the same protocols, logging in, and then the analog value, and then if it's greater than 500, or if it's less than 500, it turns on. That's it. Thanks. So some of the problems and possible future plans we had, COVID-19 prevented us to complete certain planned parts of the project. This includes like the overriding part. It does work like kind of currently. It just the conditions kind of override what you input to them. We wanted to enclose the case in plexiglass for safety, and add in a Raspberry Pi on the side of the frame as a control panel. Are there any questions?
Okay, yeah, anybody who's viewing, please submit questions on chat. I think you touched on it, but the standard question, what was the biggest challenge, and did it cause you to alter your approach?
Some of the biggest challenges that we had just completing the project, kind of like we touched on earlier, the ESPs, they only run off of 3.3 volts, so they only output that much. So we had some issues that the relays didn't want to turn on. Ended up figuring out that the ESPs can actually run from 5 volts. It was a little bit later on than we liked, but that's really one of the biggest problems that we had with it.
Okay, here's another one. Can you provide some details of the relays that you used?
I know they have the 5 volt coil voltage. They're just SP to ST, I believe. They're just some standard relays.
One thing, when I introduced this project, the last project ran pretty long, and so I was trying to get everybody enabled, and I think I neglected to mention the faculty advisors, Dr. Napamita Pal, and wanted to make sure that mention that and thank her for her contribution here. Another question, what were some social, environmental, or other impacts taken into consideration?
Some of the environmental was that it is low voltage. It is pretty efficient. to use. And take, for example, kind of like it made us want to do this project was if, say, like you're not at home, like you leave your house in the morning and it's dark outside, but you actually leave maybe your front porch light on, and like say it gets brighter outside, and it takes that natural light and it'll turn the light off as it gets brighter outside. It could be a similar concept for the fan in the temperature.
Yeah, just to add to that, one of the main goals of when we did this project was to save people money. Like Zach mentioned, when you leave your house, if it's, you know, dark, lights will come on. If it's sun rises, lights go off. It kind of controls your air conditioner as well. So that was one of the main goals we wanted to accomplish.
And just to add to that, like the weather in Louisiana, sometimes you'll leave the house and it'll be in the 40s and it'll be really cold. So you'll have your heat on. And then by lunchtime, it's in the 70s and 80s, and you don't want to come home and still have your heat on all day. And then you walk into a miserable feeling house where it's muggy and hot, and then it takes a long time to cool off, which in turn will cost you more money because you'll have to run your air conditioner at a lower setting. And then this project actually helps with, you know, starting that process a little bit sooner during the day, and you won't have to run it as low and as at a high speed to try to cool the house down efficiently. That way it will be doing it all day while you're not even there. And so in turn, saving you more money and hassle.
Another thing I can add that you can control and monitor from any place with an internet connection. So there's actually an app that you can use that KENNEL offers that we use to be able to. I actually have done it from my phone and through a web browser. So you don't have to be in the same network. It could be anywhere with the internet connection.
We have another question. How does this differ from products already available on the market?
A lot of the products in the market usually only count for, like, say there's like temperature, or just there's not really much for the offering for the lights that we looked. And there's a very rarely you'll find, like, most of the systems don't require for like multiple appliances, like your house and your AC system and stuff and so on. That's mostly just like people would pay and have that for their own network. And it's not, you can't really go out in the market and buy a system that controls everything opposed to this. And that's what we kind of are going for our project. It's something that's like, it takes everything, bits and pieces from different parts of the market and puts it all in one.
And a little bit more to add to that, whenever we were come up with an idea for this project, we kind of, as Jackson was saying, we looked into different other markets to try to see if there were any similar products already out on the market that, you know, we didn't want to create something that had already been created. So we kind of looked into it and did a little bit of research and found that, as Jackson was saying, there was nothing that really offered the complete package. So I figured, you know, that this would be a pretty good idea. Why buy 4 different products and try to make them work simultaneously and across different platforms, whenever we could just create the complete package on one and save the user and the consumer a lot more trouble and hassle whenever all they have to do is go to one place and they can control it all.
Okay, thanks, guys. That's all the questions we have. And so we will take another brief break and we will resume at 3:30 for our final presentation of the day, which will be the auto spooler.
Thank you.
Thank you.
We will get started here with the auto spooler in just a moment. We just have a brief delay. Okay, our final presentation.
Wait, I don't hear anything.
Our final presentation of the day is
I'll be
the
back. I'll be back.
auto spool.
I gotta fix something.
And well, one of the team members is having a little bit of trouble, so I guess we'll wait just another moment here. I'll remind you that those that have been with us for the other presentations, that we invite your questions and please submit them on the chat function. You see the chat button on your Zoom menu, and type them in, and then I will read off the questions at the end. Jordan, you can go ahead and share your screen. And I'll leave it up to you when to get started. Okay, Victoria's online and unmuted. So go ahead, Jordan.
Our project is called the Auto Spooler. The goals of our project were to be able to transfer wire from a larger spool down to a smaller spool, which are meant to be purchased in the school store for use in engineering projects. The project should be able to help save time for student workers so that they may be able to work on other projects, and the project must be automated. The project will be transferring wire from one spool to another so that custom lengths of wire can be easily prepared for students. And we'll be using a PLC and HMI setup to accomplish this goal.
When designing our project, our design philosophy was to be able to use materials and parts available, as well as use as many resources that our school offers. The reason we have done this is so in case any student or professor that would like to recreate our project can do so. Along with that, we would like to be as space efficient as possible so it could fit on anybody's desk.
The parts that are used for the project is a programmable logic controller, PLC, and a human machine interface, HMI. We also use stepper motors, filament extruder, aluminum extrusion, stepper motor drivers, various parts to hold it all together, and a voltage regulator. We utilize the PLC that has 8 inputs and 8 outputs so we can add more features into the future. And we chose the HMI because it directly connects to the PLC, ability to display information, and it also has the ability to implement virtual buttons. And it allows us to show how much wire we have spooled. We also use motor drivers and stepper motors. The motor driver allows us to use current control and micro stepping, and it controls the stepper motor, which allows us to precisely step the motor so we can do accurate measurements.
For theory operation, we are using the Automation Direct PLC and HMI for controlling and displaying. Attached to them are motor drivers that provides current that allows microstepping with the stepper motors. Attached to the top stepper motor is an extruder that pulls the wire down to the bottom stepper motor, which rotates the smaller spool, winding the wire around it. Here are a couple of pictures of our prototype design. As you can see, we have both a line guide and a cutter implemented on them. As for our final design, we decided not to implement the line guide since the wire layers evenly around the spool without it needed. The cutter wasn't implemented due to equipment restrictions at the time. And here's a flow diagram of our program. From the title screen, we can go to the screen select, which you can choose between either manual controls or numeric entry. From numeric entry, you can enter the desired wire length in either inches or feet. That then gets converted in the PLC ladder logic math function, which turns the desired wire length into a final position, which then moves the stepper motors to that position. So, due to the different diameters for the extruder and the smaller spool, each motor moves at a different velocity. To keep the tension between them, we had to calculate the angular velocity for them. And here's the demonstration for the HMI screen.
Presenting the auto spool. After powering on, we find ourselves on the title screen. Just a tap, it changes to the screen select. On this screen, we can choose which unit type will be entered, either inches or feet. For this demonstration, we're going to use inches. Now we are on the operating screen. Once here, we can use the numeric entry button to enter the desired length in inches. We'll be using 24 inches. Then we just hit enter. Then it's as easy as pressing start. As you can see, once the program has started, the HMI displays how much is being spooled. The HMI also has a stop button and a manual up and down button if needed. Now that it's finished spooling, green light indicates that it's okay to cut. Then new operations can begin.
And here's another demonstration of the whole system working with the middle cut of the actual smaller spool being wire winding around it. And here are the updated screens from after we made the video. We made a new screen select and added a manual motor control, which you can control either both the motors, just the bottom motor, or just the top motor. And here's the updated screen for the numeric entry. As you can see, we have both a zero out button and a progress bar at the bottom. The red line indicates the finished product, the finished percentage of the finished position. The finished position.
Some precautions that we've taken for this project were, first, we made isolated circuits. This allows us to be able to use our HMI and PLC and stop all other operations to troubleshoot. Along with that, we also have our emergency stop, so during any problems that occur during an operation, we could stop it. And lastly, we added backup manual controls. With this, we could either set up things easier through controlling it, or if there's something wrong with the ladder logic, we could manually operate operations. As for environmental impacts, it's not as applicable for this project. Our spools are reusable and recyclable, and this is a one-off project, not creating any more waste. As for future improvements, we would like to implement a cutter to further automate the system and implement an enclosure to keep the components and people safe. Not to say that our project isn't unsafe now, but to close off voltage regulators would be preferred. And lastly, we would like to integrate a PCB or terminal blocks for electronics to easier troubleshoot. And that's it.
Any questions?
Okay, the first question that we've asked all the teams, and that is, what was your biggest obstacle, and did it cause you to change your approach?
For us, I think our biggest problem was just being able to get equipment that was necessary during this time. We could have gone around this, but it would have been a significant cost to outsource it, since everything that we designed was original and not the use of pre-made parts, except for our PLC and HMI.
All right. Do we have any other questions? Please submit them on chat. This is our final presentation of the day, so we have all the time we need. Looks like they're all questioned out at this point. Okay, you must have covered it so thoroughly that there aren't any questions. So I'll move on to my wrap up. I want to thank, first of all, everybody who has been viewing and participating in the presentations. I also want to thank Dr. Hall for helping me review and approve the projects, along with consulting with and advising the teams. Thanks to the other faculty advisors for their support and guidance for the teams. And I want to especially thank the students for all their hard work, and I wish them well as they transition to the next phase in their lives. And with that, this concludes the ICET and EET senior design presentations. Thanks.